Okay, students, welcome back to the third and final part of this lecture about some more techniques in Octave. One of the techniques that you're going to need to know is how to find the maximum value of a set of values. You're going to be needing to do this in Project 1 because you're going to be determining the angle that you're going to set your solar panels to in order to get the most energy from the sun. So you're going to have tried a whole bunch of different angles and you're going to have to figure out which one is the one that resulted in the maximum energy. That's a particularly kind of common application for the for statement and the if statement and so on. Let me give you an example of that right here. I'm going to just sort of write a little piece of code here on the blue window that shows, I'm going to start off with an array called x that I'm going to be using that is defined to be from 100 elements from number 1 to number 100, just 100 integers. And let's just make y is equal to this function of x. I happen to have chosen y is equal to the sine of x divided by 15, but we could have done any number of different things. How would I find the value of x such that the value of y is the biggest it's going to be? It's the maximum across that domain, that range of x's. Okay, so you're trying to find the value of x such that its corresponding value of y is the biggest value of y. And there's a strategy for doing this here. We're going to find it and we're going to call it max. We're going to say max is going to be the biggest value of y. Notice, by the way, I'm using maxx, maxx or something, maxx. You're going to find out why in a little bit here. But you're going to find the value of y for this, the value of x. This is a little bit confusing here. I might not have been entirely consistent about how I labeled this in the red box here. We're just trying to find the value of y that's biggest. Let's just put it that way for now. Okay. So here's the sneaky trick that we do when writing a computer program that needs to find a maximum. What you do is before you start looking for the maximum in your data, you set the value of the maximum to something ridiculously small. Here, I set the value of maxx to -999. Okay. I mean, the value of y will always be bigger than that, okay? And the reason why we're going to do this is how the algorithm is going to work is it's going to go through all the values of y, and if the value of y at the location I is greater than the current max, it'll set the current max equal to that value of y. So you want it to fail the very first time. You want the very first time that it looks for, y of 1, the first column of the array y, to be bigger than this max. This is a slick little trick that is a useful trick in computer programming. So what I'm going to do then is for every value between 1 and 100, we're going to look and see what is the value of y of I. If if the ith row of y is greater than max, which it definitely will be the first time, I mean none of them are going to be as small as -999, but check them all. If it is, set the current value of max to y of I. And in this case, notice I'm using this max index variable here. Max index is then set to I. Max index is going to be the value of I where that maximum is happening. Alright, so as we go through here, as we change the value of max x, it just gets to that new value of y of I, and max index gets set to I. When we're done with this loop and we hit the bottom here, at the bottom of this loop, when we move on to the next part of the program, max x is equal to the largest value of y, and max index is what index I of y that is. So, like if our maximum value was at the value of I equals 23, and y of I equal to 23 is the biggest value, we now know that. What a slick trick. You can see how you're going to be doing this kind of thing when you're trying a whole bunch of different angles. You'll have one variable is angle, and then another variable you'll have computed as a function of angle is like how much power you're generating, and then you're going to find the angle at which you have the most power. It's a pretty slick trick. Why did I call this maxx instead of max? It turns out the word max, is already a word in Octave. You could actually, it's a function that's built in, which is a handy thing. I mean, another example of Octave already has things built in. In this particular case, Octave is smart enough to realize if you're using the word max as a variable name, it will actually turn off that function that is built in called max. So, because, if you want to have a variable called max, it won't stop you. It'll just turn off that function called max. But in general, that's a bad habit to get into. Because it isn't smart enough to do that for any time. Every time, I mean, there are thousands and thousands of possible commands and functions in Octave. You can't you can't know them all. In the case of max, they actually automatically turn it off if you're trying to use a variable called max. That one is probably better waiting until we're going to spend more time on that trick about finding a maximum when we do project 3 in the next module. I do want to talk for a little while about integrals, because there's an integral in the problem that you're doing for project 3 in the next module. You are going to be determining the solar flux on a solar panel at any given moment. The total amount of power that falls on that solar panel over the course of a day is the integral of that amount of power. Okay, so integrating over the course of a day, that's the total power that you got in the course of a day. Now, let's be more general than that. Hey, you need to compute the integral from 0 to 1 of sine of x. Okay, here's the deal. There are, in fact, some computer languages that can evaluate an integral, where it's actually like Maple is an example of one. You can actually tell it the equation is, f of x equals sine of x, and it can do things like compute integral of. But that's actually fairly rare. It's actually fairly tricky to get a computer program that can actually evaluate an integral literally, as in like it knows the rules that were in the back of your calculus textbook. By and large, they can't do that. Octave certainly cannot. Rather, it's going to be performing what is called numerical integration. And if you look at this little diagram that I attached here, it gives you kind of a sense of what we mean by that. I mean, the actual integral from x0 to x6 over there is the area under that red curve. So x is our, along our x-axis, and like an f of x or a y or whatever is on the y-axis here. Strictly speaking, the integral is, what you learned in calculus, where you have to have all those integral rules and all that kind of good stuff. Product rules and trig rules and all that kind of good stuff. But realistically, that is not something like Octave is going to know. But what Octave can do is take that area that's under the curve and divide it up into a bunch of little pieces that are each sort of trapezoid shaped. See how there's 1, 2, 3, 4, 5, 6 little pieces there? Each of them is sort of a little trapezoid, and see how you add those 6 pieces up, and you get kind of the same thing as that area. It's not exactly the same, it's an estimate of that area underneath there. But that's a type of what we call numerical integration. Okay, Octave can't literally compute the sine of x, but it can take the graph of it and divide the graph up into little trapezoids and add the areas of all those trapezoids up. That's actually not a tremendously complicated thing. I mean, it's a fair number of steps, but I've got students in other classes that have done those kinds of things. They're a common technique for computing integrals in atmospheric sciences, for example. Okay, so fortunately, as is the nature of an interpreted language like Octave, trapezoid rule integration is already something somebody has written for you. You don't have to figure out how to do it. So we can compute an estimate of this integral by dividing up that x-axis in the area under there into a certain number of pieces. Let's do it in this case here. I'm going to take this area under there and say that x-axis, the domain here is from 0 to 1. See how that's the limits of the integral? Let's divide it up into, say, 10 pieces. My x-axis, I'm going to have my variable x, my array x, to go from 0 to 1 in increments of 0.1. So x is equal to 0, 0.1, 0.2, all the way up to 1.0. Alright, then I'm going to make my function of x. F of x is just the sine of x. We're just going to be dividing that, we're just going to be making a function. F will have 11 values in it, just like x does, each one corresponding to the matching value of x. And then the integral is just ridiculously simple. It's just trap z of x of y, of x comma y. This is so slick. I mean, trapezoid rule is not that terrible. I mean, if you had to write it yourself, you could probably do it in 10 lines of Octave or something like that. But somebody did it for you, and it works, and it's been thoroughly debugged and all that kind of stuff. Man, interpreted languages are kind of cool, actually. So what does this actually do? What does it look like here? I mean, if I wanted to actually see another example of like how, if I wanted to check this, for example, here, I love wolframalpha.com. I mean, there's all kinds of powerful things you can do in there. If you're not familiar with Wolfram Alpha, go find a tutorial or something. There's all kinds of cool things you can do. So I went to wolframalpha.com and I typed in integral of sine x from 0 to 1 by trapezoid rule with 10 intervals. That's just what we exactly did with that trap z function in Octave. And Wolfram Alpha is pretty smart about figuring out what you mean when you put in a natural language request like that. And in fact, it determined that the value of the trapezoid rule integral is 0.5 0.459315. Okay, and we'll see that that is the right answer that we get as well using our Octave program here. That is our estimate here. We have computed a trapezoid rule approximation to the integral. For the record, if you actually just did calculus, you just sat there and did the integral of sine is negative cosine evaluated from 0 to 1, you get the answer is 1 minus the cosine of 1, which is 0.45970. I mean, you can see we've got this estimate is accurate to 3 decimal places. I mean, that probably is good enough. It's an estimate of the value of the integral. Wolfram Alpha does provide you with a little diagram right here that shows you what this looks like. Here's our little diagram. The solid curve is actually the graph of sine of x from 0 to 1. And it is, you know, if I had continued this farther down the axis, it would eventually make a sine wave. We're just seeing a little piece of a sine wave here. And what Wolfram Alpha has done is it has divided the x-axis into 10 little slices to make 10 little trapezoids who pretty well fit under that curve, and then just added them up. It's called trapezoid rule integration, and it works pretty darn slick. Let's actually do an example of that over here. Let's actually write ourselves a, let's call this one example 7.mat. I'm not sure where we are, so let's just start a new one. Alright, let's say I was trying to compute the integral of, over a range from 0 to 2 pi, in steps of, let's say 0.01. Alright, so, let me just make sure that makes sense. So x goes from 0 to 2 pi in these little steps, and let's just call it f of x is equal to, how about the sine of x squared? I think we can do squared like that. I actually haven't done that in a long time. Let's see if that works. Let's actually, before we go any farther, let's actually test that. It's always a good idea to test your program before you write too much of it. Let's actually try this. Octave, run example 7.mat. Got an error. Must be a square matrix to do a squared operator. Okay, that could very well be. I must have made a mistake. So let's do this here. Let's say x squared. Let's use, oh, this is good practice. Let's use our dot star x. We're saying each element of x times the corresponding element in x. x1 times x1, x2 times x2, x2 times x3. Let's make sure that works. Save it, yes. Octave, run example 7.mat. There we go. So now if I say display the values in y, or it's actually f, isn't it? Yep, these are the values in f. Alright, that worked. Okay, I'm going to bust out of this and I'm going to go back into nano. Alright, how do I want to compute this integral? It's easy. I'm going to take the trapezoid rule of x comma f. Alright, this will be our integral of the sine of x squared from 0 to 2 pi. And if we go ahead and try this here, save it, yes. Run Octave, run example 7.mat. Answer is 0.6899. Okay? That is the estimate of the integral from 0 to 2 pi of the sine of x squared. Okay, so I mean, good grief, that was a really simple way to compute an integral, or at least an estimate of an integral. It is just an estimate. We could divide the area up into smaller rectangles or bigger rectangles, and we would get more or less accurate estimates, but it's pretty straightforward. Alright, let's actually try one of these here. For your final question on this lecture, go ahead and write a little Octave program that estimates the value of this integral using a trapezoid rule with 10 intervals. So you're computing the integral from 0 to 10 of the function x plus 2 sine x, and it's going to be broken up into 10 little pieces here. I actually put it over here on the next slide here. That's what the diagram, the solid curve there is what a graph of x plus sine x is. So the integral is the area under that curve between 0 and 10. And you can see, I actually just cut and paste that out of Wolfram Alpha. You can see that the area is getting divided up into 10 little pieces, each of which is a little trapezoid. And you know, they're not quite a perfect fit to under that curve, but it's a pretty good estimate to add up those 10 little areas of those trapezoids and call that the area under the curve. Alright, go ahead and take a stab at this. Again, it's not going to take you more than a few lines, 3 or 4 lines of Octave to make this integral work. It's good practice because there's definitely going to be integration on the in Module 3 when you're doing Project 1. Give it a shot and then click on one of the 4 links below this video, depending on what you think your answer is, and I will see and give you some feedback.